Hey, grab a seat. Welcome to the team. I know, it's literally your first week, but honestly, there's no better way to learn the ropes than by jumping in and fixing a live outage together. So, in today's explainer, we're going to completely demystify Docker networking. We're going to take what probably seems like absolute dark magic right now and break it down into pure logical mechanics. By the time we wrap this up, you'll know exactly how containers talk to each other, how they talk to the outside world, and most importantly, how to debug them when they completely refuse to. Okay, let's dive into this. It's a classic junior mistake, and we've all been there. We've got this severed connection between our Python Flask app and our Redis database. Both of these containers are running. If you check their status, they look perfectly healthy. But the app is throwing this massive connection refused error. The hostname isn't resolving, the IP address isn't persisting, and the port, totally unreachable. Docker networking trips up almost every developer the first time because, by default, containers are heavily isolated. They have their entirely own network stack. So to fix our little outage here, we actually need to understand the default environment they just booted into. So when you run a container without specifying a network, it automatically attaches to the default bridge, which shows up as Docker 0 on your host network interface. Think of this default bridge kind of like a massive apartment building. Everyone has a room number, which is their IP address, like 172.17.0.2, but there is absolutely no directory in the lobby. IP to IP communication works perfectly fine. If you go in and hard code the IP address into your app, it will connect. But here's the catch. Containers are ephemeral. They stop, they start, they get updated, and boom, they get brand new IPs. Because this legacy default bridge predates Docker's built-in DNS, container names resolve to absolutely nothing. It makes connections incredibly fragile. All right, let's look at Section 1, User-Defined Bridges and Container DNS. Instead of that chaotic apartment building without a directory, what we really want is a luxury hotel front desk with a fully automated directory. And that is driven by this specific IP address, 127.0.0.11. This is Docker's embedded DNS resolver. If you poke around inside the etc resolve.conf file of literally any container on a user-defined network, you'll see this exact IP. It runs inside every container and automatically maps container names to their current live IP addresses. And here's where the real magic happens. If you scale that Redis service up to, say, 3 instances, this exact same DNS resolver will return all 3 IPs and perform round-robin load balancing for you completely automatically. So, golden rule here. Always use names, never IPs. Moving right along to Section 2, Secure Service and Port Mapping. Okay, so if a user out there on the internet actually needs to reach your web app, that port is hidden by default. We have to essentially punch a hole through to the host using port mapping. But you have to be super careful about how you do this, because the exposure changes drastically based on the command you use. If you use p3000, you are binding to all host interfaces, basically 0.0.0.0. External traffic from absolutely anywhere can reach it. Now, if you do that with an internal database, like mapping Postgres using P54325432, you have just exposed your database to the entire public internet. Honestly, in a lot of DevOps teams, mapping a database to 0.0.0.0 on a public server is literally a fireable offense. It shows up in AWS security reports every single year, causing massive headaches. For internal services, always map to localhost using 127.0.0.1, 5432. Or honestly, better yet, don't map ports at all. Just let them talk securely via the internal Docker network name. Which brings us to Section 3, Sidecars and Advanced Network Modes. Going beyond the bridge. So, most of the time you're using bridges, but there are specific times in production when you actually need to break standard isolation rules using what I call escape hatch modes. First up is host mode. When you use -network host, the container drops network isolation entirely. It just shares the host machine's network stack directly. No bridge, no NAT overhead, no port mapping needed. You'd really only use this for extremely high-performance workloads or maybe monitoring agents that need to see all host traffic. On the total opposite end of the spectrum is none mode. Using -network none gives the container only a loopback interface, 0 external access whatsoever. It's basically a locked vault. You use this to completely lock down network access for highly secure data processing or maybe batch jobs that only ever need to read from local volumes. Now, our final mode is container network mode, and this one is super cool. This is where you tell a new container to share the exact network namespace of an already running container. Why on earth would you do this? Well, because this is the exact mechanical foundation for the Kubernetes sidecar pattern.
When we eventually get you working in Kubernetes, you're going to see Envoy proxies running alongside your app, intercepting traffic on localhost right within the pod's shared network. Docker's container network mode is exactly how that pod networking illusion is built under the hood. All right, Section 4, Scaling with Overlays and Multi-Host Networking. So think about this. What happens when your web app gets scheduled on server A, but your Redis database gets scheduled over on server B? A single host bridge isn't going to help you there. You need a multi-host overlay network. When you contrast the single host bridge with a multi-host overlay, you see that overlay networks actually extend Docker networking across multiple physically distinct machines. They encapsulate container packets inside UDP packets, specifically port 4789 if you're curious, using VXLAN tunnels. So to the containers themselves, it feels exactly like they're sitting right next to each other on the same local subnet. They are perfectly able to ping each other by name, even if they're physically located in completely different data centers. This is the built-in networking for Docker Swarm, and conceptually, it prepares you perfectly for understanding how Kubernetes CNI plugins like Calico or Flannel route traffic across massive clusters. The mental model transfers directly. Finally, Section 5, the Network Debugging Toolkit. How to fix issues fast. Okay, theory is great and all, but in the real world, things break. Memorize this toolkit, and you can confidently fish for yourself during your very first midnight outage. Run these 5 steps in order. First, Docker inspect. This tells you exactly which network your container is attached to and what its IP currently is. Second, Docker network inspect. This lets you see every single container currently living on that specific network. Third, you want to jump inside the container itself and use nc-zv to do a TCP ping. This tests if the target port is actually open and reachable. Fourth, run a quick trace route from an Alpine container to see exactly where your packets are dropping. And fifth, check the host level. Use TCP dump on the Docker 0 interface to watch the actual packets flow, or use NSLookup inside the container to verify if that 127.0.0.11 DNS resolver is actually returning the right IP. Basically, this is your survival checklist. So, applying what we just learned, we created a user-defined bridge, we used the proper DNS name, and boom, our app finally connected to Redis. The outage is completely fixed. But before you pack up and log off for the day, let me leave you with one final thought to chew on. We know containers are ephemeral, right? We know they get new IPs when they restart. But what happens to the actual data sitting inside that Redis database when the container stops? Does it just vanish? Well, if you want to make sure our database actually survives a restart, we're going to need to conquer Docker volumes next. But for today, really great job fixing the network.